Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today we'll be introducing solutions. In the water molecule, we're reviewing hydrogen bonding. Then we talk about aqueous solutions, solubility of nonpolar compounds, dissolving ionic compounds, and the energy exchanges associated with the solution process. And our lesson begins on page 199 and it ends on page 204 from the text Chemistry 11 in Focus. Sparkling sodas, alcoholic beverages, tea, and a myriad of aqueous solutions that we consume or otherwise use are solutions of various types of substances dissolved in water. These solutions are created because of the incredible ability of water to dissolve a wide array of substances. Because of this remarkable property, water is sometimes referred to as a universal solvent. While most solutions are made for a usefulness, others can be made naturally that may be counterproductive to human health and the environment. Since water does not discriminate between what substances it dissolves or not, inevitably substances that are harmful to human health and other living organisms can enter its sources. Water falling through the air in the form of snow or rain dissolves gases such as nitrogen dioxide, sulfur dioxide, and carbon dioxide, which eventually falls as acid precipitation. Acid precipitations can have devastating consequences on ecosystems and infrastructures made of marble and metals. Also, water running over the surface of the earth dissolves organic compounds, mineral ions, and other poisonous substances in its path. People living in poor countries around the world with no water purification systems have no choice but to drink and use water in these impure forms. In more affluent countries where there is a scarcity of water, they even recycle water from sewage after its treatment. Their municipalities have the arduous task of purifying the water by removing most of these dissolved harmful substances from it. This chapter describes the water molecule and explains how water dissolves various ionic and polar compounds and the energy changes accompanying the solution process. It also explains how nonpolar compounds dissolve fellow nonpolar compounds. So first of all, before we go further, we need to have a quick review of the water molecule since it plays a crucial role in dissolving different types of substances. Okay? So here is the formula for water. And this is a ball and stick model of water here. It's an AX2E2 type of molecule. The electron arrangement again is tetrahedral. It's a bent molecule, 105.5 degrees at bond angle, and it is a polar molecule. So here we see how these bonds here are having bond dipoles. And now in the end you have a net dipole there with that end of the water molecule acquiring a small negative charge and this end here becoming slightly positive. Okay, the polar OH bond. We learned that if two atoms have a difference in electronegativity greater than 0.4, then the bond becomes a polar covalent bond. And you can see in this case here, oxygen has an electronegativity of 3.5 hydrogen 2.1, and now because of that, there's a big difference in electronegativity of 1.4, and that makes the OH bond polar. So polar molecule, we've spoken about that already when we did bonding. Okay. Of course, we also spoke about hydrogen bonding that exists between certain types of molecules, and water is one of them. And this is a question I always give my students. I ask them, look, the molar mass of water is 18.02 grams per mole, and that of carbon dioxide 44.01 grams per mole. You can see here carbon dioxide is nearly 2.5 times as heavy as water, yet carbon dioxide is a gas and water is a liquid. I would ask them to draw these molecules and from that deduce which one is polar, which is non-polar, and based on that, they are able to say why this guy here is a gas and that one there is a liquid. And it has to do, first of all, with polarity of the molecule. This molecule here is non-polar, but this one is polar. Therefore, carbon dioxide molecules will only be attracted to each other by weak London dispersion forces. So the force of attraction between the molecules are not strong enough to keep them as a liquid, whereas both the molecules being polar are held together by hydrogen bonds as well as London dispersion forces. That is why water is a liquid at room temperature. So here we're showing you now how hydrogen bonding takes place in liquid water and ice. On the left, we see how the molecules are held by hydrogen bonds. These molecules here, see, these are hydrogen bonds here. Okay. And the water molecules here, you can see they are arranged in irregular patterns. You can see that. There's no fixed pattern here. How does water evaporate? Water evaporates when these molecules gain enough kinetic energy from some source, and maybe heat or something, and they're able to snap these hydrogen bonds here. They snap these here, and that's how water evaporates. Only right now, you can see the water molecules here are arranged in regular hexagonal arrangement. And this is what happens when you cool water below 0 degrees Celsius. Ice is formed, water freezes. Okay? And here you see they're arranged in these regular hexagonal patterns. And of course, they're still held by these hydrogen bonds here. It is because of these open spaces like what you're seeing here that makes ice less dense than water. Water here as liquid. And because of that, ice floats in water. All because the water molecules are arranged in a different way that creates more spaces between the molecules than in this side here. So these molecules here make the water of a higher density than in the case of ice here. And that's why ice floats in water. That has some ecological significance because ice floats in water, but the water beneath allows living organisms such as some species of fish and algae and so on that have adapted to live at low temperatures survive. So that is the difference between the arrangement of the water molecules in liquid water and ice. So now we're going to talk a little bit about aqueous solutions. So a solution is formed when a solute is dissolved by a solvent, okay? So you get what is called a solution here. In aqueous solutions, water is the solvent, and water has the ability to dissolve ionic compounds and also polar covalent compounds. So what we'll do first of all to show you how it dissolves polar covalent compounds, and we use methyl alcohol in this example. I took the Payne's Billing model of methyl alcohol here. That's the formula for methyl alcohol, CH3OH. In this case, right, you can see carbon is the central atom there. And it has 4 bonds. These will be the 3 other bonds for hydrogen. This is the O, and that is the OH bond here. Of course, oxygen will have 2 lone pairs here. Because this bond here is polar, the OH bond is polar, that end of the methyl alcohol molecule acquires a small positive charge, and the oxygen here has a small negative charge. So what will happen here then is slightly positive hydrogen here will form hydrogen bonds with these lone pairs of electrons on the oxygen. Same thing happens here. Okay, this water molecule from this one here forms a bond with the lone pair on the oxygen here. And because of these hydrogen bond there, methyl alcohol dissolves in water because the molecules are able to attract each other by hydrogen bonds. So that is how a polar covalent compound dissolves in water because of hydrogen bonding. And most covalent compounds do not dissolve in water. Only a few of them dissolve in water. Reason for that is due to the fact that they're not polar and therefore they do not support any dipole-dipole attractions or hydrogen bonding between themselves and water molecules. These pictures here they have here will help you to understand a little bit more. This is water here, and they pour a little blue food coloring inside. The coloring dissolves in the water to make it look blue, right? Over here is a little bit of vegetable oil. In here, the water molecules are held together by hydrogen bonding and London dispersion forces. And in here, all molecules are held together by only London dispersion force. When you mix them together, look, because oil is less dense than water, it floats on top. That's why I color the water there for you to see this demarcation line here. Because these molecules do not have any polar bonds, and these are polar, they do not attract each other. And that's why this oil will not dissolve in water. That's why you have an oil spill, right? The oil will remain floating in water and can have lots of ecological consequences. Okay? These have some applications too. If you have some greasy things on your hand, you try to wash that away with water, it will never happen. The water will slide away from the grease if you don't have soap. If you do not have soap, you will have to get another non-polar solvent to dissolve that grease away. Sometimes you take gasoline and you wash it away. So non-polar things will dissolve non-polar stuff, but polar substances will dissolve polar substances. So this diagram here is showing you how covalent compounds that are non-polar dissolve fellow non-polar ones. So let's say that these guys here are solid molecules and these are the solvent ones, okay? The theory is that because they're all non-polar, why gasoline will wash away the grease from your hand is because of London dispersion forces that exist between the solvent molecule here. See this here? Positive charges are induced here because of instantaneous dipole, and it induces dipole over this side, and it's happening all over the place here with lightning speed. That's why a non-polar solute can be dissolved by a fellow non-polar solvent. We had a peek into this already, how an ionic compound dissolves in water. Of course, we know that the ions in an ionic compound are held together by strong ionic bonds. So we'll go through again the processes that are involved in getting an ionic compound dissolved by water. So first of all, know that water exists like this. They're held together by hydrogen bonds. You have to first of all zap these bonds to free up these guys there. You have free moving water molecules, right? In every case, all these molecules are held together by hydrogen bonds. So some energy, first of all, must be used to break these hydrogen bonds here and to free up these molecules here, because we'll need them now to do the next process. So breaking of the hydrogen bonds entails the use of energy. Dissociation of the ions in the crystal. I allow you to read this because I'll use the figure beneath to explain that. Okay. Here are our free water molecules. All right. That's why you broke the hydrogen bonds there just now. So what you're seeing here is a part of an ionic crystal of sodium chloride. Here you can see, it didn't show that, the sodium and chloride ions are bonded by these ionic bonds here, all right? And these are relatively strong. And the strength of these bonds here depends on two things. In any ionic crystal, it depends on the charges on the ions, In this case, we have a sodium ion with one positive charge and chloride with one negative charge. You could have a calcium ion with two positive charges, and you could have an oxide ion with two negative charges. That's one of the factors that will determine the strength of the ionic bond. And secondly, there's something called an interionic distance, right? The distance between the center of this ion here and the center of that ion here. When you do Coulomb's law, depending on how far these ions are, such will be the force of attraction here. A third factor is the way these ions are packed in the crystal. There's something called lattice energy that is involved. I don't want to get into that. So we have the charges and the ions, the interionic distance, and the way these things are packed in the crystal. And all of these will contribute to what is called the stability of an ionic crystal, okay? So these are several factors that are holding these ions together and maintaining the integrity of the crystal. Now let us explain what is happening here now. You can see, because of this positive charge here, the water molecules are attracted to that sodium ion there. So you can see how the water molecules are oriented around the sodium ion. The water molecules orient themselves with the negative end towards the positive sodium ion there. Each one of these is exerting an attractive force on the sodium ion. And the cumulative effect of all these large number of small forces being exerted on the sodium ion eventually rips it away from the crystal. It's like the Lilliputians tying down the giant Gulliver. So I don't know if you read that book. All these small charges here eventually overcome the attractive force between this sodium ion and this chloride ion there and pull them out of the crystal there. Same thing will happen here. Only difference is that the water molecule will orient themselves in such a way that the positive ends now are directed towards the chloride ion to bring about that attractive forces that will pull that away eventually, and you get your free chloride ions there. Okay? So this is how water dissociates the ions from the crystal. Why it is called dissociation and not ionization? Because these are already existing as ions. Any process that separates them is referred to as dissociation. And of course, that needs energy. Talking about energy, if you heat a crystal up in water, it facilitates its solubility because heat makes the crystal lattice becomes unstable. It's giving these things more energy for them to vibrate farther away from each other, and it weakens the bond there, and therefore the water molecules are able to rip these away with much more ease, and especially some crystals that are sparingly soluble in water. The moment these ions are out, they become immediately surrounded by water molecules due to electrostatic force of attraction between them and the polar water molecules. And this processes release energy, and we call that exothermic change. Those two first processes are referred to as endothermic changes because energy was absorbed during that. Now this is what happens here. Because this guy here is positively charged, look, only water molecules will orient themselves in such a way that their negative ends are facing the positive ion. Because of that, this guy is suspended in the water. This is what makes these ions stay afloat in the water. If you didn't have these, they would have sunken to the bottom. It's like you have a series of lifeguards holding up a swimmer who doesn't know to swim, okay? Same thing is happening here, okay? But the water molecules are oriented in the opposite direction to attract that. And this process here liberates energy, okay? So this is called solvation of the ions. So this is how an ionic crystal dissolves. First of all, the hydrogen bonds are broken. Secondly, the ions are dissociated from the crystals with the use of energy. And finally, once the ions are dissociated, they're solvated by the water molecules there. You call it specifically hydration energy because you're using water, all right? If it was any other solvent, you call that solvation energy. Now I just want to go back to explain to you something that we did before. See, remember when we did that symbol displacement reaction? We said that magnesium displaces guy, and this guy sunk to the bottom of the test tube. But magnesium become part of the solution. This is the explanation. Look, magnesium gives up 2 electrons and becomes an ion. Okay, these 2 electrons here are accepted by the copper ion and becomes a copper atom. So look at this diagram here. This is before displacement. The copper ions, see the copper ions, they are being attracted to the water molecules, so they were in solution, they were dissolved, right? They're part of the solution. When you accept these 2 electrons, what happens? It is changed to a copper atom. Now there is no existing force between these water molecules. See, nothing there is there. And that is why this guy, without anything to hold it up, sinks to the bottom as a precipitate. Now you see what happens? Magnesium was an atom, okay, which couldn't dissolve in water, but because it forms an ion now, look, it gets solvated by the water molecules. I said, as I'm doing this, let me just take the opportunity to explain why copper was precipitated and why magnesium became part of the solution. What is happening here, look? See? These are the anions. They're surrounded by water molecules here. These are the cations here. They're surrounded by water molecules here. So bear that in mind. Okay. Energy changes is significant for us. Now listen to me. The first 2 processes, breaking of the hydrogen bonds and the dissociation process, absorb energy. The solvation there released energy. A solution process can either be exothermic, where heat is produced, or it could be endothermic, where it absorbs energy. Listen to this. If the amount of energy absorbed from the first 2 steps is less than that released from the 3rd step, the process is exothermic. Okay? Because the 3rd step is giving off more energy than the energy used in the combined 2 first steps. And examples of this is when you dissolve certain compounds such as sodium hydroxide in water. Now, another thing about this is that when you dilute concentrated acids in water, it is very, very exothermic. So you should take all the precaution when diluting. When you want to dilute some concentrated acid, don't pour water on the acid. You're looking for some serious problem. When you do that, the heat produced will cause the water molecules to boil spontaneously. And it's so violent, it can bring particles of the concentrated acid out too, and it can burn you. And then you have the solution process whereby energy is absorbed. If the first 2 processes absorb more energy than is released, there's a net absorption of energy from the environment into the solution, and that is an endothermic change. And this is what happens when you have things like ammonium nitrate and stuff like that are used. Because of this ability to create endothermic changes, certain compounds are used in making coal packs. That's how it is made. You pack some ammonium nitrate in a plastic bag that's delicate. And then you place this plastic bag into another more sturdy plastic bag that has water inside, and you seal it up. And when there is need to use this coal pack, what you do, you pressurize it. When you pressurize it, you cause the inner plastic bag there to burst, and it releases the chemical there, which is this guy, and it causes this whole thing to become cold. Hand warmer is also used in the same principle. Instead of that, you can use something like calcium chloride, for example, and when that happens, instead of absorbing heat, it will release heat. In case you're somewhere where it's cold in the winter, you need to warm your hands, you do that. We want to talk about dissociation versus ionization. What we saw how sodium chloride gets dissolved in water is called dissociation. The ions are already there, but they just separate, and it's called dissociation. Okay. Ionization now is when you have a molecule and you dissolve that in water, you produce ions. For example, when you have hydrogen chloride gas dissolved in water, it ionizes, and in that case, you get hydrogen ions and chloride ions. You have non-aqueous solutions too, where you have different solvents dissolving different solids. So in this case, you can have a solid dissolving a solid, where this is a solvent here, where in gold jewelry, silver gets dissolved in gold, okay, or carbon gets dissolved in steel. So these are solvents here, and these are the solutes. You can have a liquid and a solid, where the liquid is a solute, and the solid is a solvent. Gold, for example, is a solvent, and it can dissolve mercury to form amalgams, gold amalgam, when you extract gold. So what they do, miners and so on, when they have the gold there, it's mixed up with other substances like rocks and stuff like that, they pour mercury there, and the gold, they'll dissolve the mercury to form the gold amalgam there. And of course, mercury and gold gets mixed up there. That's why when you take that type of gold now to the goldsmith, he will heat it up using a blowtorch, and the mercury will escape as a gas. I've seen that thing happen in a local goldsmith in my village. They didn't know about the effects of mercury poisoning. They will just be standing there, and they have this thing, and all this smoke is coming out, and they're inhaling this gaseous mercury and stuff like that. And I used to be standing there. We never knew that at that time that what was coming out here was so poisonous. And then you had the solvent is gas, and the solute is liquid, water, in air. Okay, you got fog, and then your gas in liquid, carbon dioxide dissolving water, making carbonated drinks, oxygen in water for respiration, gas in gas, oxygen in nitrogen, oxygen in helium, in scuba diving, and then of course you have liquid and liquid. I don't want to talk about this here. Alcohol. Okay? Alright. That's why my little brother died on the road. A drunken driver killed him, 17-year-old kid. Alright? So I don't want to see this guy at all. So you have mixtures now. You have two types of mixtures. A mixture is for when you add together two pure substances. Some mixtures are homogeneous mixtures, like when you take salt and you dissolve it in water, you shake it up, the salt gets dissolved, you look at it, you only see one phase. Okay? You have heterogeneous mixtures. When you mix these things in water, they do not have a uniform appearance, and you call these heterogeneous mixtures. They have blood, milk, salad dressings, so you know more than I do. These are examples of homogeneous mixtures. Show how the ions separate there when dissolving in water. Okay? There are other types of homogeneous mixtures too when you dissolve these guys in water too. Okay? All right. So here are some activities for you to do. All right. Sorry about this. On the solution, these are repeated in the solution manual, and the answer to these are provided. I hope that was helpful. See you again.